In this video, we'll look at 2005 AB1 from the Form B test. It's another area volume free response question. So we have these two functions f of x and g of x defined as they are in the problem here, and R is the shaded region in the first quadrant enclosed by the graphs of f and g as shown in the figure above. The first thing that we want to do is to find the area of R. So before we can do that, however, we do need to find the points of intersection here. So we're going to have to use the calculator to do that. So I'll bring up the graphing calculator. And we start off with y1 being 1 plus sine of 2x. And go on to enter y2 is equal to e to the x over 2 power. And since f of x, or y1, is on top, the area is just going to be y1 minus y2. We still need to find the points of intersection here. So I'm going to go out to zoom standard, see if that gives us a good window to see this. Not too good, so I'm going to adjust my window instead to go -3 to 3 for both x and y, and we'll take a look at that. Alright, so we can see the area between the two curves in the first quadrant that we're interested in, and I'm going to find my points of intersection. Second calc, option 5 for intersect, and the first curve is the sine curve, second curve is the exponential curve, and guess we get essentially that's x equals 0. It's -8.47 times 10 to the -16th. So that's the point 0, 1. And we'll go on from there to find the other point of intersection. So second calc, option 5. We'll move a little off to see which curve we're on. We're on the sine curve, so that's the first curve, second curve. We just want to make sure we're closer to the second point of intersection than to the first, and it will automatically gravitate to that one. So the x value is 1.1369. And so I write those points of intersection down on the curve. I have x is equal to 1.13569 and y is equal to 1.76446. And I'll show you how we can, especially the x coordinate we're interested in. I'm going to go back out to the home screen, and here I'm going to just say x, and if you wanted to see what that was, that is the 1.13569, etc. I'm going to do x store into a, and that just saves that value so I don't have to type it in all over again. Right, so we're going to the 0 and 1 are fine, but the other two are a little bit more complicated. And I can do the same thing with y. And so y is just above the 1. And notice that's the 1.76446, etc. So I can do y and store that into letter B. Now, it's already in y, but what happens is that whenever the calculator, both the x and the y variables are system variables, so they're used, and if they get used again before we need them, they'll get overwritten with a different value. So we have the values we want stored in A and B, and I can even write that onto my worksheet. And from this point on, I can simply reference those constant values instead of writing those whole numbers out or typing them into the calculator all over again. So all we need to do now is to set up our integral. We go back into y equals. We're going to turn off the two functions, and instead we just want variables, y variables, function y1 minus variables, y variables, function y2, and that's what we want to integrate. I'm going to go back out, and if you recall, we have math. Option number 9 is fn int, variables, y variables, function. It's y3 that has the function we want to integrate. we put in the variable of integration, and then we're integrating from 0, and instead of typing that number all over, I can just hit alpha a, and that will give us 0.429. So as yet I haven't set up the integral for part A, and I'll do that right now. All we need to do is set up our integral from 0 to a, and in this case I don't have to even write out 1 plus sine 2x, because that is clearly defined as f of x minus g of x dx, and at this point I just simply need to give the answer that we found on the graphing calculator, rounded to 3 decimal places, which is the rounded to 3 decimal places, again, which is the answer to part A. So we'll go on to part B here. For part B, we want to find the volume of the solid when R is revolved about the x-axis. So, and to do this, I'm just going to paste another smaller copy of the curve that we've been working with, of the graph that we've been working with. And the first thing that we're going to do, we're going to revolve both of these curves around the x-axis. So you can see that the inside curve will have a radius of g of x, while the outside curve will have a radius of f of x. And we'll give them a little thickness, and that is our dx there. So all that we need to do here is to add up those washer volumes from 1 to what we call A. And so you recall that this is, the area is pi capital R squared, or the outer radius, minus pi little r squared, or the inner radius. And so capital R in this case is our f of x, and little r is our g of x. So if I was to then set up my integral, it would be pi, we'll bring that out in setting up the integral, times the integral from 0 to a again, I don't have to restate what that is, of f of x quantity squared minus g of x quantity squared dx. And we'll bring in the graphing calculator to calculate that value. So we go back into the y equals screen, and I'm not going to change y3. We'll start our new function as y4, and that will be pi times the quantity variables, y variables, function y1 squared minus variables, y variables, function y2 squared, close parentheses, and all we'll need to do is integrate that from 0 to a. So we'll go back out to the home screen, recall the last command, and all we need to do is change y3 to be y4. Oops. And variables, y variables, function y4, and we're ready to go. And that turns out to be 4.267 rounded to 3 decimal places. And so that gives us the integral for part B. We'll go on to part C now. Close down the calculator. For part C, we have the region R as the base of a solid, extending for this solid, the cross sections perpendicular to the x-axis are semicircles with diameters extending from f of x to g of x. And this time I'll draw a representative strip right onto the original, and we're going to make that a semicircle and find the surface area of that semicircle with a little bit of thickness, which would be a dx, and then there would be an infinite number of those from 0 up to a. So what we recall that the area of a semicircle is pi r squared over 2. But in this case, the radius itself is f of x minus g of x over 2. And so we would have to plug f of x minus g of x over 2 in for r in the area of the semicircle there. And you notice that when you do that, not to clutter up the space with a lot of math, but we can do it down at the bottom here. We have room for that. We're going to square that. We'd have area is equal to pi over 2, maybe easier written that way, times f of x minus g of x, quantity squared, over 2, quantity squared. When we square the 2 in the denominator and bring it out, what we really are going to have there is pi over 8 times f of x minus g of x, quantity squared. And so that's all that we're going to need for this. We'll set up the integral for part C to be pi over 8, integral from 0 to a of f of x minus g of x, quantity squared, dx is the thickness to each one of the cross-sectional areas, cross-sectional volumes there. And that's it. So you really want to look at the difference between A, B, and C. They all involve f of x minus g of x, but they're all used in slightly different ways and produce slightly different volumes. So we'll call up the calculator again and go back to y equals. And this time we'll turn off y4. We'll start a new function, and that would be pi over 8. Oops. That would be pi over 8, and then times y1 minus y2 quantity squared. Variables, y variables, function y1 minus variables, y variables, function y2, quantity squared. And that's all we're going to need to do. Now our function is y5. We're still going to accumulate that from 0 to a. So we go back out to the main screen. All we have to do is bring up our previous function and make sure we change variables, y variables, function y4 now to be y5. And execute that, and we get 0.078 rounded to 3 decimal places. Now recall, this is not a volume of revolution here. This is simply cross sections coming out of the base of the region R that we see there. And so we expect this to be much smaller than either of the other two volumes of revolution. 0.078 rounded to 3 decimal places. And I'll close down the graphing calculator, and we have the 3 different parts to this problem. Remember, with a free response question on the AP test, you, especially with the calculator part, you need to be able to set up the integral, or whatever the problem is, set it up mathematically, and then use the calculator to find the answer. So all that you're going to be graded on is what you see there for parts A, B, and C. And obviously, to get the full credit, they have to be exactly or correct. Okay, that'll do it for this video and this problem.